All right, hello. This is the midterm review for Lecture 1, the basic concepts of embedded systems. So to start, we first need to define what an embedded system is. And from the lectures, the formal definition for an embedded system is a controller programmed and controlled by a real-time operating system with a dedicated function within a larger mechanical or electrical system, often with real-time computing constraints. And so the key takeaways from this four definition are listed below. It's that embedded systems are typically programmed during their development, and they're not meant to be programmed or flexibly used by the end user. So that means that they are programmed for a specific task in mind. The counter example of this is a general purpose system, such as a desktop computer. Those are meant to be used very flexibly by the end user. The end user could use a regular desktop in a large number of ways, and the desktop computer isn't restricted to a single task. It can be flexibly used. Going back to embedded systems, they're typically part of a larger system, hence the name embedded, and their job is to either record or react to events in real time. So here's a couple of examples of devices that use embedded systems. To the left, sorry, we have a quadcopter, which has devices such as an IMU or motor drivers. And so these devices are embedded systems that are meant to allow the quadcopter to detect its position and respond accordingly. Inside of an AC unit, you would typically see a temperature sensor as an embedded system. And so this temperature sensor allows the AC unit to react to the ambient temperature of the room, allowing it to either turn on or turn off, depending on how hot or cold it is. And additionally, we have smart lights. I've never actually owned one of these devices, but I'd imagine that inside of them, you'd find a Wi-Fi or Bluetooth communication module. So this embedded system allows the device to communicate with other devices through Wi-Fi or Bluetooth. So when designing embedded systems, there are three key factors to design for, and that is low power, high performance, and low cost. We want to design for low power because embedded systems are typically integrated into a larger system. And this larger system probably has either a small power supply or it has devices that are already drawing a large amount of current or power. And we don't want our embedded systems to draw too much power to take away from the rest of the system. So ideally, we want low power. And keeping in mind the real-time aspect of embedded systems, we want to aim for high performance as well. This will allow our embedded system to meet tight timing constraints and respond quickly to the user or the environment, keeping things real time. Finally, we want our embedded systems to be low cost because, well, nobody likes things that are expensive, and we want to decrease the cost of these devices. So looking back at our three examples from earlier, in terms of designing for low power, you would imagine that the embedded systems in a quadcopter would want low power because a quadcopter probably runs off of a battery, and you don't want to drain that battery too quickly or else the product is undesirable. For the AC unit, you could imagine that the rest of the AC unit is already drawing a large amount of current, and we don't want our embedded system to put too large of a strain on the power supply. As for the light bulb, of course, we don't want this light bulb to draw too much power or else it becomes undesirable compared to regular light bulbs that are more power efficient. In terms of the real-time aspects, quadcopter, it needs to react quickly or else it's going to fall out of the air if it's not able to respond to its position fast enough. The AC unit needs to be able to react to the ambient temperature in real time in order to apply proper feedback and maintain a constant temperature within the room. And the light bulbs need to be real time in order to quickly respond to the user. The user doesn't want to be waiting a long time in order for something to change. That's, again, undesirable as a product. And all three of these devices need to be cheap in order to be competitive within the market. So we want to keep our embedded systems as cheap as possible to not increase the price of the rest of the system. And so there are also a couple of related concepts to embedded systems that the class should be going over, and that is IoT. The main idea behind an IoT system is that you take multiple embedded dedicated function devices that operate and communicate together through communication protocols such as Wi-Fi or Bluetooth, and this allows you to use multiple devices at large distances. Additionally, embedded systems validate the idea of ubiquitous computing, which is the idea that computation will increasingly move into all sectors of the world. Computations can take place in any form, anywhere, any purpose. Embedded systems can also be used in cyber-physical systems. So these are devices that process information digitally and then and also react to the real world through physical systems. And additionally, they're used in cyber-human physical systems, in which you take the system that we mentioned earlier, a cyber-physical system, and introduce a human interface so that a end user can interact with the real world and the rest of the system. And so we want to study embedded systems because there are a couple of key benefits that we gain from using embedded systems, and that is improved data collection. So as you have a large number of IoT devices that can be used across large distances, you're able to collect data that was previously unattainable, or you can collect data at higher frequencies, or you can collect data that's just of much better quality as these devices become lower cost and in higher quantity. Additionally, there are a lot of AI applications that come with embedded systems. By using embedded systems, we're able to allow very high performance, high resource intensive AI systems to interact with low-level tasks that previously would be very difficult if we stuck with the typical large processor, large resources, cloud-based AI. And we have a couple of examples of these here. So in terms of collecting more data, you can imagine that with a large number of IoT-enabled devices, this comes in handy when you're studying areas like the forest. You could imagine an airplane flying over a forest, which is typically very hard to navigate on foot, and just airdropping a whole ton of embedded system and IoT devices into the area. And then all of those devices will communicate with each other and with a much larger cloud server system, and collect data that would previously be unattainable if you stuck with the typical one device system, and at higher frequencies and at much better qualities than you would previously find before. And finally, in terms of AI, here's an example of a smart home. With a very large power cloud-based AI system, it would be very difficult for it to, say, control a door, turn on your lights, control your windows, look at the remote control, etc. And so by embedding devices all throughout this smart home, this allows the high resource intensive AI system to interact with these low-level tasks. And so that concludes the first lecture. Good luck to everyone on their midterms. Peace out. Eat.